All right, we press on here, chapter 13. So, um, excuse me, this is our second class of biomolecules. So, if you'll remember the first one, right, was carbohydrates. And so again, we're just talking about organic compounds here that are bigger than the ones we encountered in the first half of the class. Lipids are no exception. So we'll start. Let's start here. And you got a little information in this slide. I wanted to point something out here with the laser pointer. When we're thinking, okay, so there's a definition there: heterogeneous class of compounds or of biomolecules. The idea here is that heterogeneous, right, means non-uniform throughout. If we think back to like Chem 3 and 3A and how we would talk about mixtures, chemical mixtures, right, being homogeneous or heterogeneous. Homogeneous, uniform throughout, heterogeneous, multiple parts that you can actually distinguish between. And I'll point that out here in a second when we start to draw our first lipid. But if we're thinking about the class, this is, I think, is just from probably a Bettelheim from our textbook. It's like, okay, here are all the sections we could go through. We're going to focus on this first section and this last section. So lipids in those categories. Now there are others. We just, again, we can't get to all of it. And we actually see talk a little bit more about vitamins later in the nutrition chapter. So that's like a good thing that we can push to a later date. The prostaglandins, leukotrienes, thromboxanes, those are really interesting compounds. We just don't have time to really get to them. So, okay, so let's do this. Let me get a pen here. Make sure it's a black pen there. Okay, so what I wanted to do is okay. So here's what I want to do. I want to start with a compound. This is technically a lipid. So let me draw it. You're gonna recognize this though. Okay, now you may not know what it's called, and I'll just write what it's called here. This is stearic acid. And by the way, this is like, sometimes you'll run across this when you're doing your reading, or you probably will when you do your reading. There are these so this hopefully we recognize as a fatty acid. Now it's excuse me, it's relevant to talk about in this chapter. Well, first of all, because it's a lipid. And we can say, okay, well, why is it heterogeneous? And I know there's a bunch of things we're kind of talking about all at once. So let's just remind ourselves of something though. There's what we call really what amounts to a polar or let me try to get this hydrophilic region, right? If we want to think about, I was just trying to. Right, this region, right? I should have just circled it, maybe, right? Just circle it, that region, right? And then there's the other region, which is this region, and this is really non-polar, hydrophobic. And so in that way, this is a heterogeneous molecule, meaning we have two sort of regions of the molecule that have different properties, both chemical and physical properties. Now, one thing I was just getting to, I kind of got sidetracked there, is if you ever encounter this notation where there's two numbers separated by a colon and they're describing a fatty acid, generally speaking, the first number there is the number of carbons. And the second number is the number of units of unsaturation, or we'll just put number of double bonds. Okay, and typically, as we'll see, those are cis double bonds. And of course, this fatty acid, stearic acid, excuse me, has no double bonds. And so, that's why that number is 0. Okay, so just a couple things again about fatty acids that we might remember, and then talking about why that is in this class of molecules. Again, it's heterogeneous. Now, another one, by the way, the fatty acids are simple. So I'm just going to put this is a simple lipid. So we'll talk later about complex lipids. We can make a distinction. There's actually different ways of like defining what a simple and a complex lipid simple and complex lipids are. I don't know if I really want to get into that, but another type of simple lipid that I want to show you, it's a really important one in our chapter, is a triglyceride. So let's look at one of those. So triglyceride, or sometimes I'll just put AKA triacyl glyceride. Sorry, that's a Y. Triacyl glyceride, or even more shorthand than that, or another way of saying this, we'll often just call these, because it's kind of a mouthful, triacyl glyceride, we'll call them tags. Okay, so triglycerides or triacyl glycerides are tags. And if you've ever had your, excuse me, if you've ever had your blood, like a blood test, one of the things, a cholesterol test or a lipids test, one of the things that often is part of those blood lipid tests are tags or triglyceride tests, and of course cholesterol, which we'll talk about later on as well. So one of the things, okay, so acyl, I don't know that we've encountered acyl before. Maybe we've mentioned it in our organic chemistry portion, but acyl really just means carbonyl. So there's 3 carbonyls, and they come from, as we'll see, 3 fatty acids being esterified to glycerol. So really these are, come on now, triglycerides or triacyl glycerides or tags are triesters made, let's say, from glycerol plus 3 fatty acids. Okay, hopefully we can use FAs from now on. We've done that before as well. It's just shorthand for fatty acids. So if we let's just make one. First of all, here's glycerol. Okay. Okay, this is an alcohol backbone. Okay, so what we might remember, again, Fischer esterification, sorry, is when we take an alcohol and a fatty acid, we put them together, we form an ester, right? It's a reaction we've seen, in a number of different places. So if we take, for example, let me just draw out 3 fatty acids. I'll give you their names. You don't actually have to memorize their names or know their names. If you need them, I would give you a table or whatever. But this is the deal. So if we take 3 and this is kind of, I'm stepwise putting this together because I want you to, one of the big things in this chapter, I know here's a bunch of asides here that I'm kind of giving you along the way. One of the big things in this chapter that we focus on is structure, and then of course we relate it to function because there's a biology component here as well. But we're trying to, like, for the first part here, get a handle on the structural features of these different types of lipids, and I definitely want you to latch on to this stuff. Okay, so let me draw a few fatty acids here. I'll draw stearic acid again. I think there were 18 carbons, right? 3, 4, 5. Okay, that looks good. So stearic acid, I'll just write that here. Another one, well, again, there's so many different types here. I think this one's called palmitoleic, if I remember right, the one I'm going to draw now. I was thinking 16. We'll do something with 16 with a double bond. 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, shoot. I'm not sure if I got that second. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, I'm going to try to draw that again, actually. Just because it was kind of wonky the way I drew it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's not much better, but it's a little bit better. And it'll help us to, start to talk about cis double bonds and how they form kinks in these structures. But okay, here's another one. So I think this is palmitoleic. Again, not that that's so important. And then let's draw one with a little longer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20. So the 20 ones with no double bonds, I think this is like arachidonic, or I think it's arachidic acid. Again, the names are not so important here. Now, remember what we have here, and let me switch over really quick so I can highlight this with a laser pointer. Remember, we have an alcohol and a carboxylic acid. Same thing here, same thing here. And if we bring those two together, right, we can make essentially 3 esters, and that's where this triesters description comes in. Because now, if I'm going to go back to the pen and put it all together and show you what we end up with. We'll kind of put it all together down here so we have enough room. And then I'm going to just draw everything that was there. So the first one was steric, right? So that was 18O, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I don't know why I keep missing a carbon there. One, two, 3, 4. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we'll do the other one, which I think we said had 20, right? 2, 3. 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 8, 10, 12. Okay, all right, seems okay. So what we're saying here, and let me point out a few things here. This is now a triglyceride, or a tag, right, that was formed from the glycerol backbone, right, the alcohol trialcohol essentially, and 3 fatty acids to form a triester or a tag. Okay, now one thing too I'll mention here is that these tags, I don't know where to write it here. I'll just put tags often contain one or more fatty acids with a cis double bond. So we'll just put one or more unsaturated fatty acids. So in this case, the example was the palmitoleic one. Palmitoleic acid, acid here. And notice also, let me just say this, double bonds in naturally occurring fatty acids, so there's that FAs are generally cis. Okay, remember, cis double bonds versus trans. And I know this is kind of a crappy looking double bond down here, but hopefully we can see that it's cis as well. And they create, and this is going to be something we'll talk more about in here in a little bit when we talk about, all of a sudden I was just hoping, I'm just going to make sure that we're actually recording here. For some reason okay, we're still going. I just got this funny feeling that maybe we weren't recording, and I was just talking to myself. But okay, so where was I? We were saying, oh yeah, we're going to talk about how these cis double bonds create kinks in these chains and how those things influence physical properties. So, all right. Also, I just want to say this tag. Let me get a black one here. Is also a simple lipid. Okay. Now the next thing that we're going to do, so I guess I hadn't even clicked over here or come over to the slide yet, and you see again most of the stuff we've just discussed, and you see another rendering of a triglyceride. Notice too here, I'll just point this out, it's not a big deal, but sometimes you'll see that second fatty acid kind of pointed in a different direction. Remember, there's free rotation around these bonds, so technically that could happen easily, and does in certain situations. So okay, so let's see here. What's next? Probably complex lipids. Let me go back to the pen. No, not that. Let's see. Why did I have an extra? Yeah, okay, that's fine. I guess I just have an extra page there. Okay, so now, that was, I guess, a good segue into our discussion about physical properties. Now, I will say this. just as a reminder of something we've discussed before, hopefully you remember talking about fats and oils. And I think we did that in our, I think it was in our carboxylic acids chapter where we encountered soap molecules, right? And we were talking about how soaps really are made from fatty acids. They're basically made from lipids, and triglycerides as well, actually, as we'll see later on. But anyway, I guess what I wanted to point out was, remember what we said was sometimes these big long chains have kinks in them because of double bonds, and that allows them, or I should say doesn't allow them to pack together, as well as the saturated fatty acid chains, the ones with no double bonds. So what you see here, right, when we're thinking about, so right, if we're thinking about this, right, we have an oil, and here we have a fat. Now, technically, they're both fats, but we normally say oils are fats that are liquid at room temp. And again, we've written this in our notes before, but anyway, okay. So solid at room temp. Okay, both have lots of lipids in them, and both have triglycerides in them, actually. And what you'll see is, actually, that's illustrated here as well, right? So triglycerides rich in unsaturated fatty acids, right? Oils, and the other ones are semi-solids or solids. We call those fats. Now, the question is why? We've really looked at examples of this. So let's just say that the why has to do with, remember, so let's say fatty acids, and I'll just put in tags, I'll just put by themselves or in tags, equal either free fatty acids, or in tags, we just said how these can be incorporated into tags that have cis double bonds, i.e. unsaturated ones, don't pack together, as well as saturated ones. Okay, and so let's say this. You know what? I wonder if I have a, yeah, okay, I have a slide here. So let's continue this idea here. Sorry, it's kind of split between two slides. So let's say better packing, right? Or more efficient. Remember, yeah, maybe more efficient packing together. Or let's say this. When fatty acids, again, those are free or incorporated into triglycerides, when fatty acids pack together more efficiently, they do, or they have more, we'll just put dispersion, right? Because these are nonpolar chains. So dispersion interactions, right? Which leads to a higher melting point and boiling point, right? But in this case, we're talking about liquids versus solids. That corresponds to a higher melting point, right? When fatty acids, I think this is probably apparent, but go ahead and we'll go ahead and write it. When fatty acids don't pack together efficiently, right? So as is the case when they contain cis double bonds. So unsaturated fatty acids are the ones we're talking about. They have a they participate in less dispersion interactions. they have less dispersion interactions, and that leads to a lower melting point, right? So we're talking about, right, solids at room temp here and liquids. I'm just trying to put all this together for us. So solids at room temp, or fats, and then liquids at room temp. Wow. Try this again. Liquids at room temp, or oils. Okay. And if you want an illustration of that, right, if we're thinking about, if we're just thinking about, and don't, let's not count carbons here. Let's just kind of show. Let's just show some fatty acids that are kind of like close to one another. Whoops. To illustrate this. So that's the idea, right? The chains are, you know, we're talking about this situation here, right? The chains are, they don't have any cis double bonds, so they pack together really well. And so we could put, like, you know, little red dots here to indicate there's a lot of dispersion forces right along the, you know, where those chains come together, nonpolar regions of the chains. By contrast, right, if we think about, you know, this situation where we have so we have there's like an unsaturated fatty acids, right? So here's another one. I meant to write a carboxylic acid group. So, and then maybe here's another one. Again, we're not worried about which ones these are or even counting carbons, but you see they just don't pack together quite as well, right? Now there still would be some dispersion interactions, but they might be weaker. They might be, you know, that fatty acid chains might be farther apart in most cases, right? They just don't pack together as well. So what we're saying is this situation is the one described right here, right? So that's the situation we're sort of describing there. So it takes less thermal energy to pry them apart because their interactions aren't quite as efficient, or there aren't as many of them, right? So that's the idea. Okay, so okay, all right. So let's start talking. I just want to make sure we're not missing anything here that we wanted to maybe discuss. Yeah, you know what? I just ran. I was just thumbing through this, and I recognized also there was a statement about solubility and fats, you know, as we know, right? So we're just thinking about oil and water, right? They don't mix, right? And I'm hopeful that we can recognize that even though these things have a lot of times polar regions on one end, the bulk of these molecules are really, really non-polar. And there it is right there. I didn't even see it underlined when I was kind of talking. But I want to point it out, right? Most of these are not water soluble. They're because such a large portion of them is very non-polar. Okay, and we just talked about the melting point part, but I hadn't addressed the water solubility of these, which is very, very low. Again, for reasons we've discussed. Yeah. So back to here. Okay. So next thing is, and this is a really nice diagram, and excuse me, we'll do something kind of similar, but maybe we'll add some more detail. This is nice. So I like this diagram because it kind of it's kind of cartoony, but it illustrates how the structural differences between the types of complex lipids that we're going to encounter now. So it's a nice thing to refer back to if you'd like to. So next thing we'll do is we'll do kind of a, like I said, a similar flow chart, but then in that diagram we'll add some detail, and then in each of these different types of complex lipids we need to look at, I guess, separately. So let's start out here, and let's say two main types of complex lipids that we'll talk about. Let me just put two types, because these are two types that we're going to talk about. Two types of complex lipids. People might take issue with that otherwise, but so we'll talk about phospholipids and glycolipids. And these are broken down further into what we call glycerophospholipid and sphingolipids. Okay. Whoops. Sphingolipids. Okay. Now, so let me just write a few things about each of these, and then again we'll actually draw them out. We'll look at specific examples of these, and I'll point out structural features. But as the name maybe suggests, right, if we're looking at glycerophospholipids, we're just talking about glycerol, so maybe that's familiar to us. Phospho sounds like phosphorus, and it turns out there is phosphorus in these. There's a phosphate group in them, and then they're obviously lipids. So the way we'll start out is we'll say, okay, all of these have an alcohol, what I like to refer to as an alcohol backbone. So again, if we're going back here, you see the backbone is in purple in all of these, and so or that's what I call it, the backbone. I can't remember what Bettelheim calls it, but alcohol backbone, and that in this case is, like we said, glycerol. Again, we'll put this together here in a little bit. Now, another thing I like to keep track of is the number of fatty acid chains. Okay, and if we're thinking about like what we just drew, like a tag, right? A tag had 3 fatty acid chains. It turns out that these glycerophospholipids have 2 fatty acid chains. Okay, attached to the backbone, and we'll talk about that as well. And then there's also, like we said, a phosphate group. You know what, let me do this. Number of fatty acid chains attached, I was just thinking of, to alcohol backbone, just to be a little more descriptive. Okay, there are 2 of them. And then the next thing I want to say is there's a phosphate. Okay, so there's a phosphate plus alcohol also attached to the alcohol backbone, and this alcohol is one of 3 types, 3 possible alcohols that I'll mention. One of 3 possible alcohols here. So the reason I so phosphate plus alcohol attached to alcohol backbone, I want to say that this phosphate plus alcohol is also referred to as a phosphate ester. Okay, so a phosphate ester, let me just draw one down here. We'll actually see this, and I'll just say, okay, well, let's just pretend there's a minus there, and then an O, and then an OR. Why does my R do that? An OR. Come on. Okay, so the idea is this is a phosphate ester, right? If we do an aside way up here at the top, remember, this is a regular ester, right? And I just put like this. I just meant for it to be like whatever over there. This is a regular ester. right? And what you see down here is a phosphate ester. It's the same as a regular ester, except for notice there's a phosphorus there instead of a carbon. So just something, again, I want you to know or be aware of. Now, I kind of boxed myself in, so I'm going to move this over a little bit. Oh, man. Just to give myself a little more room. Sphingolipids. Okay. Now, sphingolipids are similar to glycerophospholipids. Again, if we go back to here, you'll notice some similarities, but there are some significant differences. Come on. There are some significant differences as well. So, alcohol backbone is not glycerol anymore. It's, again, the name suggests this. It's sphingosine. Okay, because it doesn't, I think because I'm down low here, it's really sensitive. So sphingosine. Okay, and we'll look at sphingosine when we draw these out. Now, number of fatty acid chains. Attached to alcohol backbone. Sphingosine in this case. Whoops, backbone. I'm going to put 2, and I'm actually going to put a little asterisk here. The reason I'm going to put an asterisk there, I'll point this out when we draw these. One of the big long hydrocarbon chains, which I refer to as a fatty acid chain, is actually part of sphingosine. Anyway, yeah. So more to come on that. I'll point that out, but I will put a little asterisk there, because it's not actually 2 separate fatty acids that you're adding here. It's one's already part of the sphingosine backbone. And then same thing, phosphate. This is where this is similar to, I should say, the glycerophospholipids. So phosphate plus alcohol. Whoops. Again, 1 of 3. Possible, same thing here, as the glycerophospholipids. Again, this whole thing is called a phosphate ester. And I should have put attached to alcohol backbone, just to be clear. I'll get rid of this here. Attached to alcohol backbone. Again, phosphate ester, and we'll draw these together. Now the third class, the glycolipids. This may sound like glycogen to you, or something that's related to a carbohydrate, and if you kind of picked up on that, you were right. Because the deal here is the alcohol backbone is the same as that of a sphingolipid, so it's sphingosine. And then we've got a couple of same thing fatty acid chains, but instead of now a phosphate ester being I should say attached to the alcohol backbone, it's typically it's either glucose or galactose, so a monosaccharide. So let's write that out as well. So let's put alcohol backbone. In this case is sphingosine again. Just give myself a little more room. Okay, sphingosine. And then same thing as the last one, number of fatty acid chains attached to alcohol backbone. We'll again put 2 in this case as well, because it's excuse me, because it's sphingosine. We'll put a 2 with an asterisk and talk about it, and then come on. And then the last thing that I wanted to point out here for glycolipids is that instead of a phosphate ester, it's actually a monosaccharide. Is attached to the alcohol backbone. A monosaccharide that is attached to the alcohol backbone. Okay. All right. So okay. So I thought we were gonna. Okay. So there's a couple of slides here, and this is really relevant because we've just sort of described phospholipids in particular, and they happen to be the one of the main ones that's incorporated into cell membranes. So we'll say a few things about what we call lipid bilayers or cell membranes, and I think I have a couple of questions about that as well here. The lipid bilayer, and let me get a laser pointer here. Something you may have encountered in a biology class. In fact, you probably have. And what we see here is is actually, if we follow these like purple circles with the little yellow squigglies on them, those are actually meant to be phospholipids. And again, we can come back to this after we've actually drawn a phospholipid and say, oh yeah, I see. It's those fatty acid chains that are kind of attached to the backbone, and then there's that phosphate ester, and really that is what characterizes these little what we call polar heads, or these purple circles. And then if you think about it, it's the non-polar, because you have two sets of these pointed towards each other, it's the non-polar regions that are kind of pointed towards one another. And then you have all of these different things that are incorporated into the cell membrane, like transmembrane proteins, glycoproteins. So you've got, it looks like these oligosaccharides attached to the transmembrane proteins, and we'll see later on that there's cholesterol that's part of the cell membrane. We'll actually talk about how that increases rigidity, structural rigidity of the cell membrane, and those types of things. So anyway, just some things to kind of keep in mind. And again, we said we're worried about structure, but we also want to talk about function as well. And this is really relevant stuff, because I know for a lot of you, because I know you have a lot of biology to take, and a lot of you are in the health or life sciences. So it's good stuff. It's a lot of really helpful stuff. And I want to say a few words about the hydrophobic effect here in just a second, which is highlighted here. I need to go back to the pen so I can actually, having trouble moving between slides, or at least when I want to. When I don't want to, I don't have any trouble. But anyway, here's some questions, and the answers are presented for us. But the question is, okay, why are these bilayers fluid? And one of the things, and I wish I didn't have transitions there, so, but anyway, if we come back to this cell membrane, one of the things that I want us to realize is that the interactions, and we just kind of went through discussing this, the interactions between these nonpolar regions are dispersion interactions, right? So they are weak interactions. Right, we illustrated them when we were talking about fats and oils with those little red dots. Remember, dispersion forces are the weakest of the four types of intermolecular forces that we talk about. And so for that reason, these little purple circles with the little tails on them, these glycerophospholipids, can actually move past one another. So that's really the first thing is, okay, why is the lipid bilayer actually fluid, right? It's not completely rigid. It's because these phospholipids can actually move past one another. So it is kind of like a fluid. It's kind of like a liquid membrane in some sense. And that's illustrated there as well. So again, weak intermolecular forces. Okay, now the next question was, why is it called a 2D liquid? And again, the answer is presented for you here, but the idea is, remember, let me go back to here. If I were to try to take, let me get a laser pointer. If I were to try to take one of these, let's just pretend I'm talking about one of these phospholipids, and actually I wanted to flip-flop it to the other side, I couldn't do that, or I should say that wouldn't happen spontaneously, because this polar, remember, the interior region here is very nonpolar. Maybe I should draw this out here in a second. I'll do that. The interior region is very nonpolar. The exterior region is very polar or hydrophilic. And so to be able to take one of these and bring it to the other side, you would actually have to flip-flop it, bring the polar region through the non-polar portion of the membrane, and that doesn't happen easily. So again, hopefully that's something that, because we've talked so much about intermolecular forces, again, flip-flopping isn't a possibility. So we call it a two-dimensional liquid, and again, that's all part of this. You see the title of the slide, the fluid mosaic model. So again, we're kind of putting the cart before the horse in some ways here, but let me just pretend I draw a little cell membrane. Okay. Now, one of the things you'll often, again, if you've ever encountered these, or you know, you will if you haven't in a biology class, a lot of times you'll see. Sorry, I'm not great at talking and drawing at the same time. So let me just draw really quickly, and then I'll say some things. Okay, so let's pretend this is a cross section of a lipid bilayer. So part of the cell membrane. Okay, so really what a couple of things that we're trying to illustrate are the interior, right? Interior region is very nonpolar or hydrophobic. And then the exterior, both on the top and the bottom, we would say it is polar. You know, we'll just put a polar or hydrophilic environment. Okay. Now it turns out that when you have molecules, so if you put things that are heterogeneous, right, like these lipids, meaning they have a polar and a nonpolar region, and by the way, before I forget to say this, I'll get back to that in a second. These little tails, as we'll see, are fatty acid chains. Notice the kink in them. That comes from, as we've talked about, a cis double bond. So I just want to point out why they're often drawn like this. And sometimes, like, if we'd never taken a course like this one, it's just like, wow, that's weird. There's two tails, one of them's like kinked, or sometimes two of them are kinked, but often it's one straight and the other one kinked. And we're going to discuss that, but again, that kink is from a cis double bond. Now, back to if you have these heterogeneous compounds like lipids, right, like these glycerophospholipids, that have a polar and a nonpolar region. The polar regions often, or I should say the nonpolar regions often aggregate or come together just spontaneously because, again, they're kind of allergic to water, right? They're hydrophobic. And so that's what we call the hydrophobic effect. And it really is, it governs how lipid bilayers form, how some proteins form. Remember, we talked about micelles when we talk about soaps. That's true as well of micelles and how they come together. So let's actually write that. I know the hydrophobic effect was on that other slide, but I actually want to make sure we actually kind of, I don't know, describe it well. So hydrophobic effect. Let's just say we'll just say the propensity, or yeah, that's fine. For nonpolar molecules, we'll just put or molecules because we're talking about molecules with both. So molecules with nonpolar regions we'll just put fold. Sometimes they fold depending on what like proteins do, or aggregate in such a way as to exclude water. Okay, because water is very polar. So that's the idea here, water which is polar. So let's just say this is the driving force behind, sorry, it's getting kind of ugly there, the formation, of let's say lipid bilayers and some proteins and micelles. Those are the ones we've talked about so far. Some proteins. These would be particularly proteins with hydrophobic regions, and that's something we get to later. So some lipid bilayers, some proteins, and micelles. Okay. So now let's come back to specifically if we go all the way back here. Let's specifically discuss each of these classes of complex lipids, and let's at least give one example of each. Okay, so let's say, okay, so you see some information here. We'll discuss all that as we write these out. And notice again, I want to point this out. Here's a glycerophospholipid, and notice in many cases, sometimes you see both of them kinked, but like for this one here, right, there's a polar head, and then you see two chains. One of them is kinked, one of them is more straight in this case. So anyway, these are the things that we were just referring to, polar and obviously non-polar. Okay, polar hydrophilic, non-polar hydrophobic. So okay, so back to this. Okay, so let's say this anatomy. Because we're going to start with the first one on the far left on that other one. So anatomy of, let's say, a glycerophospholipid. And of course, this is a phospholipid. I think I drew that out, right? Phospholipids and glyco. Yeah, okay. Phospholipids. There we go. That's like the anyway. So if we're boxing these, right? Phospholipids and glycolipids, and then there are two types of phospholipids that we'll discuss. Okay, so back to this phospholipids, but specifically glycerophospholipids. So let's say first, remember when we were describing these that we said, right, glycero means, again, we're talking about glycerol. Now, a lot of times we'll actually, when we do this, we'll point one of these, and a lot of times it's that top one, just because again, then the rest of this is the polar part, and then the non-polar part is going to be over here. So a lot of times we'll remember there's free rotation around these bonds, so we'll just kind of tweak it a different way to kind of show it differently. Okay, so let's now remember, two fatty acids, and let's make one of them straight and one of them kinked like we were doing before. Or like we just described is often the case. So we'll do stearic acid again because it's a common one. I'm remembering how many are in it right now, so that's a good thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18. Okay, so there's that one. And then remember, let's do a kinked one. I think oleic acid has like 18. Oh, what happened? Oh no. How'd that happen? 3, 1, 2. I don't know. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Stay there, please. Okay, so now let's do this other one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's see. I think I got that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Okay, so notice again, cis double bond, that's an unsaturated fatty acid. I think it's oleic acid if I remember right. Let's not worry about writing the actual names, just in case I wasn't right. Okay, so now the other thing that I want to point out over here is that I've got a phosphate, and a lot of times I want to. Okay. Now notice here that I've actually drawn H's. So technically this is phosphate, right? If we do another aside, you guys remember PO4 3 minus. We make you memorize this in Chem 3A, and if we were to draw the Lewis structure, it would look like this O minus. And then O minus, and then O minus, PO4 3 minus. But a lot of times I'll draw it because again, the way these form in a the way these form, what I'm trying to say is the way these form actually, if we were to make them in the lab, would be much different than the way they form in the body. And sometimes these O's over here on phosphate are actually, they have H's on them. So I just want to illustrate it like this because that way I can say, okay, when we pull these things together, let me get a actual, like, let me get something red. We've done this so many times. We say, okay, let's pull a water molecule out, right? And if we pull a water molecule out, then this oxygen just becomes attached right where that one was, and then everything's connected. So we can think about this as one of those condensation type reactions. Now, I'm gonna put keep doing that. I'm gonna put this. So we've got glycerol, right? Glycerol. And I guess I could have written that here. Glycerol. Plus, here's 2 fatty acids. Remember, there were 2 of those. So 2 fatty acids, one saturated, one unsaturated. Here's our phosphate. Okay. Now, again, I know it's dihydrogen phosphate, I guess, technically, but that's just helping us illustrate this. And then the other thing, remember we said, again, I want to come back here and just point this out so to show you where we are, right? The alcohol backbone was glycerol, right? The number of fatty acid chains, 2. Then we had our phosphate, so I drew that. And now there's an alcohol. Now, I want to give you the possible alcohols, excuse me, and that's going to have to be another aside here, but that's okay. So 3 possible, wow. 3 possible alcohols that, again, writing while I talk, it's hard for me. Some of you are great multitaskers. So 3 possible alcohols attached to alcohol backbone. Okay, I'm just going to put in glycer, since we're doing this on the other one as well. So glycerophospholipids and in sphingolipids. So we don't have to restate that later. Okay, and these are them. Okay, so the first one, one possibility is choline, and I'll just draw out choline. I'm trying to remember I think there's 2 carbons. Yeah. And then there's actually a quaternary nitrogen, so there's a positive charge, 4 R groups attached, if you'll remember. So positive charge on nitrogen there. So that's choline, and then serine so this is choline. Let me write the name of it. And then serine looks like this. It's actually an amino acid. No, not like that. It's actually an amino acid, so we encounter serine again later in our proteins chapter. Sometimes this has an H on it, sometimes it doesn't. It doesn't really matter here. So serine. And then the other possibility would be one called ethanolamine. And there are actually, we'll just leave it at that. So these are the only ones we'll encounter. So this one's called ethanolamine. So it's like ethanol, right? CH2, CH2OH with an amine on one end. That's like why, well, that's why we call it ethanolamine. Okay, so there's ethanolamine. Okay, so now let's just choose one. Let's pretend now we have ethanolamine. Okay, so I'm going to draw it here, and I know I'll put it all together. Hopefully, if I have room, I'll draw it small enough. But I was trying to show you how this whole thing comes together. So there's the NH2. So notice ethanolamine. I'm trying to give you all the parts. And again, it could have been serine, it could have been choline, but we just chose ethanolamine kind of arbitrarily. And let me go ahead and while we're at it, okay, so let's say, okay, now this, right, we pull a water molecule out there. And again, why not do the same thing here? That's why I kind of drew it like that, right? Fischer esterification. And here, now again, it doesn't happen exactly like this in the body, but if we pull out all of those water molecules everything gets attached like we're used to seeing it get attached. The result now is our glycerophospholipid. So let me try to draw it. I'm gonna have to try to do it a little bit smaller, but I think we can do it. So let's do this. So O. Then O, and then that's attached to, sorry, let me make that a little bit bigger. Okay, there's that, and then, where was I? Yeah, I need to go here, right? And then I've got my ester functional groups. So, and I think there were 18 carbons. It's just kind of, doesn't look very great. There. 3, 4, 5, 6. Okay, and then we're almost done. Try that again. All right, so this result, right, of all of that being put together, those different component parts, the 2 fatty acids, the glycerol backbone, right, the phosphate, the ethanolamine, the result now is what we call a glycerophospholipid. And again, we have remember we said it's kind of like this if we think about it, right? And notice how this is that polar region up here, right? And if I'm getting my laser pointer, right, this is that polar region which corresponds to this circle here, and then this is my straight fatty acid, and that's this one, and this is that kinked fatty acid, or this one. And these are those things, remember, that make up our these lipid bilayers, our cell membranes that we're referring to. Okay, so let's go back here. Again, I'm gonna. Okay, yeah, and here you. Okay, well, actually, those were I'm sorry, I was thinking maybe that was it. Yeah, okay, so glycerophospholipids. Here we go, and then some of that is summarized here in this picture as well. Okay, next one, sphingolipids, right? Still, we're talking about a phospholipid, complex lipid that's under the phospholipids category, because we're going to see that there's still a phosphate group. But the backbone is one of the main things that's different. So let's look at these now. And the first thing I want to do, because again, the main difference here is that we're talking about a different alcohol backbone. You probably saw it on that last slide. Let's not worry about the dashes and the wedges. Stereochemistry, I suppose, is important in certain situations, but for us, we're just trying to get our bearings here. So let's put anatomy first of all. Anatomy of a sphingolipid. Okay, so here's sphingosine. Let's see. I think there are like 1, 2, 5. Let me see. I'm trying to remember how many. 2, 3, 4, 5. There's a double bond there. 6. 18 total, and yeah, okay. I think I got that right. OH, and then there's an NH2 here. And let me actually draw that out. Yeah, I'll just draw out the H's. I think that'll help us as well. Okay, now, so this is sphingosine. I just want to make sure I got that right. 1, 2, 3, 4, 5, 6, 7, 10, 11. Yeah. Okay. And again, don't worry about the dashes and the wedges on the amine or on the alcohol functional group. Yeah. Okay. Let's just draw regular bonds. Okay. So this is sphingosine. Okay. And it's an alcohol. Of course, there's actually 2 OH groups, but this is the alcohol. I should say this one here, the one on the far left, is the one that we're most interested in, because again, what we just said. Remember, if we go back here, right? These are the alcohols that are attached to either glycerophospholipids or sphingolipids all the way back, right? So we've got this sort of descriptor here. So we have that phosphate ester with one of those three alcohols. Now the one thing that I want to point out here is on that slide I had drawn an asterisk next to the fact that there are two fatty acids. One of the reasons that I did that is really there's only one, and I'm going to draw it right here. And again, it doesn't matter. Let's just use like stearic acid again because it's easy. Okay, so 2, 3, 4, 5, 6. Now we're starting to put together the sphingolipid. Okay, so here's again our fatty acid here. Okay, and again, stearic acid doesn't matter. But so notice there are two fatty acid chains, but only one of them came from actually an additional fatty acid that gets esterified to the sphingosine backbone. So that's why I put an asterisk. There are two still, right? You see this big chain up here as well, but this was already part of sphingosine. So anyway, that's why I made that distinction. So let's think again about, okay, let's pull a water molecule out. Okay, and what's formed, hopefully when we put this together, you'll recognize that really the thing that forms here is not an ester, but it's an amide. Okay, all right. So next thing, same thing. Let's bring our phosphate just like we did before. So here's our phosphate, or our dihydrogen phosphate, just to make things easier on ourselves. So there's our phosphate again. And then again, one more of those alcohols. Let's choose a different one this time. Let's choose, I don't know, let's choose serine, just because. We'll put it here. I'm trying to draw it backwards if I can accomplish that. And then this would be a NH2. Okay, and again, that's an OH, and my OHs are kind of messed up here. Let me just redraw them. And you know, very much like we just did. Let's do this. Okay, pull a water molecule out. We attach right there, and do the same thing here. We'll do the same thing over here, right? Put this whole thing together now, and the result is I'm just going to sort of draw the whole thing kind of all at once, and we can maybe say a few things at the end about it. Let's see, would be just putting it all together, making those connections that we just circled. Let's see, oh, yeah. That reminds me, there's something else I want to mention too. Okay, and then let's get our nitrogen or our hydrogen. We're gonna kind of do this upside down. That makes it easier to draw the amide functional group. Okay, so so this now is the result. Now is our sphingolipid. Okay, now a couple things. This right here, right, this is kind of new and different. It's an amide functional group, remember? Instead of like the esters on the other ones that were what was formed when those fatty acids were attached to the alcohol backbone. Again, I'm just going to write this is serine, one of those three possible alcohols, but again, it could have been ethanolamine, it could have been choline or ethanolamine or serine. We just arbitrarily chose serine. Now another thing, okay, so another thing that I want to point out here, let me just, I don't know if I did it over here. Yeah, I guess I didn't do it over here. So notice here, okay, so I want to do this real quick. Let me just get a different color. Let's do green this time. Notice that that's a phosphate ester, and if we're circling this, that's also a phosphate ester. So I'm going to write phosphate ester and another phosphate ester. And the whole thing is technically called a phosphodiester bond. because there are two of them, diester bond. And the reason I want to point that out, I know it got really cluttered and I apologize for that, but the reason I wanted to point that out is because we encounter phosphate esters and phosphodiester bonds in a lot of different places in biology and biochemistry, and they're really important. They're actually part of the thing that brings nucleotides together, or I should say, they help bring nucleotides together to form something we'll talk about later in the course, a polymers called DNA and RNA. So we see them in a lot of different really important places. So I wanted to point that out. And if we do the same thing here, right? There's our phosphate ester. And here's another phosphate ester. Actually, let me circle the R group as well, right? Because I guess it has to include a R group. So same thing, phosphate ester, and then the whole thing is a phosphodiester bond or linkage or whatever you want to say that. Okay, and then this whole thing is called now a sphingolipid. And it's another type of complex lipid. Okay. Now, the third class, and let's see what we've got here. Okay, so the third type, I should say, of complex lipid, again, back to our classification, it was the one on the far right, was again sphingosine backbone, right? 2 fatty acid chains. One of them's already part of the alcohol, but 2 total. And then instead of that phosphate ester that we were just talking about, the idea here is now instead of the phosphate ester, we put a monosaccharide. We wrote that into that classification. Typically, it's either glucose and this is listed here. You see that it's either glucose or galactose. So I want to do that with you as well, of course. And by the way, these are certainly also very much like glycerophospholipids, a part of cell membranes, and this is really cool stuff because. Later on in the chapter, we'll discuss this as well, but often sugars, monosaccharides, oligosaccharides, polysaccharides are actually cell surface markers. They're ways that things recognize, sometimes it's a bad thing, viruses recognize them, but other things can recognize them as well, that part of our signaling pathways in our cells and in our bodies, really amazing stuff. So these are important as well. So let's do this. Let's do like, I have that? Yeah. Let's do anatomy now of a glycolipid. Anatomy of a glycolipid. So these again, let's do just what we did. I'm going to redraw sphingosine here. Let's see. I hope I have it. Well, let me move it over just a little bit so I make sure I have enough room. Okay. Let's see. I keep doing that. 5. Come on now. 1, 2, 3, 4, 5. 12. Okay. Then my N. H2. Well, let me draw out the H's again, just because, again, we're going to do the same thing we just did. Because, again, I don't know why I'm missing letters here. Anatomy of a glycolipid. So same thing again with these glycolipids. Again, they're the same as sphingolipids, except for that part that's on the top left here that we're going to draw, the part where we add the monosaccharides, what I'm trying to get at here. But let me do just what we said earlier, right? Let's add now another fatty acid. Doesn't matter which one. I don't know why it keeps doing that. I think it's a different one, maybe oleic acid. But and now, okay, so now this is a little bit of just a reminder, or maybe it's a good helpful little way to quiz ourselves. It's not, so remember, these monosaccharides exist, as you know, primarily in their, this is so ugly, sorry, in their cyclic hemiacetal form. So they're closed form, right? So I just want to draw, because again, this can be glucose or it can be galactose, but let's just do galactose. We do so much glucose. So here's galactose. If you'll remember, I think it's like OH and then 2 on the left. You can check me on this, but I'm pretty sure that's right. Okay, so I wanted to just remind ourselves, okay, so if we put this into our cyclic hemiacetal form, I guess what we would do, right, is we're saying, okay, we close it like that, right? So we would have 6 atoms in the ring, so automatically we would draw our pyranose. Oops, there we go. And then we would do, let me just make that a little nicer. 1, 2, 3, 4, 5. And since it's D, we would put CH2OH. And let's just call it, I don't know that it matters. Let's call it beta. It could be alpha or it could be beta. In this case, it'll be easier to kind of draw out, I think, if we draw it beta. So then we'll put H here, and then let's see, it would be down, up, up, right? Down, up, up with our OHs, and we'll put our H's everywhere else. And so I guess we would call this then beta D galactopyranose. Just again, I wanted to just do that with you because we've done it a bunch already, but just to kind of give another example, a reminder. So beta D galactopyranose. Okay, so here's how this all comes together, and I don't think this will be too hard to envision. Let's get our red again. Again, we've got our OH and our H. Let's pull a water molecule out of here, connect those up the way we often do. Same thing here. And once we do that, we'll have a good representation of a glycolipid. Okay, so let's put it all together. Let's give ourselves a little more room. So I'll start with the. Well, yeah. Let me just redraw the. Just make sure I have enough room. H. Okay, and then what I'll do is that'll be a little bit curved, but that's fine, and we'll connect this now to the sphingosine is what I'm trying to say. Okay, back to, I guess I need an OH there, and then an N, H, and we've got our amide again. Now, the one thing I do want to point out, right, is that we've created, and we could have written this on that slide as well when we were kind of describing, what a glycolipid is. First of all, let's write that, glycolipid. But I want to make sure we recognize right there we've created a glycosidic bond. So in this case, it's beta, remember, because we said that this galactopyranose was beta. And that's the glycosidic bond right there. Remember that first bond from carbon to oxygen coming off of the monosaccharide. So we'll call this a beta glycosidic bond. Okay. And of course we have an amide functional group, right? Just like with sphingolipids as well. Yeah, I think that was those are the main things. I wanted to see if there's anything else that I wanted to mention here. Again, yeah, you see that these are incorporated into cell membranes, and there's just an example of that here as well. Okay. All right, let's call that the end of the first part of the chapter. We'll just stop there for now.